We have seen that our magnetization is the result of the sum of the individual dipole moments of all the molecules that are present in our voxel. Now the molecules in general, and certainly at our body temperatures, the molecules are moving around. They are diffusing around. So we have diffusion, we have motion of the molecules during the MR experiment. And I want to first discuss the nature of this motion, and then we will go into the description on how this affects the MR signal. So here we have a random path, we have a molecule, and this will undergo some random path. Or in more general terms, we start at a time 0, the molecule is here, and after time delta, it will be at a certain distance displaced from its original origin. This is the effect of self-diffusion. So if we look at here at an example, we have, for example, a time delta which is 100 milliseconds, and in this case, this gives us a mean displacement of the molecules of roughly 20 microns. If one waits for a longer time, of course, the molecules will diffuse further away, and here we have then a distance of 45 microns if we wait a half a second. So the molecules will diffuse further away on average than with longer time. And here, if we take an example of 1 second, then the mean displacement is 63 microns, and this gives a larger extent of the motion. This random motion diffusion was described by Einstein. It's the Einstein random walk, and this mean displacement is given by the square root of 6 times a constant d times the time big delta. D is called here the self-diffusion coefficient, and r is the root mean square displacement after delta seconds. So the self-diffusion coefficient depends on a number of parameters. Partially depends on it depends also on the size of the molecule, how easily does it diffuse. Smaller molecules move more than bigger molecules, and we're going to illustrate this in the following experiment with 2 different types of fluids to illustrate the effect. So what I'm going to do is I'm going to take some colored alcohol here, pour it in, and we can see how it starts to distribute the color. And here on we have a colored water solution. I'll pour it in, and now we can see the clear difference. On the alcohol side, it's already distributed, so fast diffusion. The color has already distributed, whereas with the water we can see this is going to take quite some time until the color is evenly distributed. We can see it has now several minutes have lapsed, and we can see that on the alcohol side it's uniformly blue, so it's very well diffused, whereas for the water colored solution that we put in, it still hasn't mixed with the uncolored water, so it's very slow diffusion on this side. This illustrates the effect of molecule size on the diffusibility of the molecule. Okay, so we've seen that molecules move. We've seen it in the experiment with the dyes. They move. This motion can depend on molecule size. But now the question is, how does this affect the magnetization, in particular the phase? We've seen that bulk motion affects the phase in a coherent manner, which allows us to determine the velocity of a molecule. And we'll go here and we'll stick with the same principle. We're going to look at the magnetization phase in complex plane. And we're looking here now at an experiment. We'll do a 90-degree pulse. We'll just, for simplicity, assume it's a 90-degree pulse. And now we'll turn on a gradient in any direction, x, y, or z. You can call it whatever you want. It doesn't really matter. What is important here is it's the same strength in both cases. One's positive, one's negative, or negative and positive, and the duration is the same. So the area is the same for the 2 gradient pulses that are applied. As we have seen before, this is in terms of magnetization phase for molecules that don't move, is a dumb experiment. The effect of the gradient is nil. There will be no net phase accrued after these 2 gradients for a stationary molecule. So let's look at the stationary case. Graphically, we'll have after the 90-degree pulse, we have the magnetization all in phase. The 90-degree pulse flips them all, and they are all collinear. and we've just plotted here 3 positions along the gradient. Now, during the gradient period, indicated by the letter B here, so we turn on the gradient, what now happens is that the magnetizations undergo a phase evolution depending on their position, and that's indicated here by the 3 positions. Then comes the period C, and this period C, we just wait a certain amount of time, so nothing happens, we still have the same phase, and we're neglecting relaxation here in the consideration. And now finally comes period D, we turn on the gradient with opposite polarity, so we turn it on, and now what happens is, since the gradient has opposite polarity, the 3 magnetization positions, the magnetization at the 3 positions, will turn with the same precession velocity, the Larmor frequency, but in the opposite direction. And after the duration of this gradient, so this area is equals to this area, or for the same amplitude, the duration is the same, they will all be aligned again as in the original position. And this is what I said, this is the dumb experiment. There's nothing interesting going on here. We have echo formation, of course, which is a nice feature. Now let's look at what happens if we allow the magnetization to undergo motion. So we start out with the magnetization stationary. Here we turn on the gradient pulse, so we have the encoding, so we have the different phase. In this case, the experiments are the same. And now during period C, we will assume that there is motion of the molecules. So, and as you can see, the colors have changed. So the blue molecule is now where the yellow was, or the orange was, and the orange is where the blue was. So we are assuming here that the molecules are being displaced. In this case, a very simple situation to illustrate the principle. We've just interchanged the position of 2 of our magnetizations here. So these are the 2 that we have interchanged. Now what happens when we turn on the positive gradients? We change the polarity. Now the blue one will rephase with the precession velocity corresponding to this position, but it has not had initial phase that corresponds to this phase. So it will actually overturn here, whereas the orange one, which had a bigger phase to start with from this position, now will only go back according to the blue position here, so it will not completely turn back. Now, can you guess what the effect is on the net magnetization? Consider here, there's no motion, we have nice echo, we have maximum amplitude. Here we have the magnetization vectors are no longer collinear. And since what we are observing, the total magnetization, is the sum of all magnetizations in our voxel, the voxel magnetization is reduced. So as a consequence, the effect of diffusion, which happens here during time period C, is to reduce the signal amplitude. We have assumed here in this whole procedure that the time C is long compared to the gradients. This is not like it's drawn here. We'll assume this is very short, and this is relatively long. So we'll only consider motion during the time period C. Okay, so now I want to do this with magnetization vectors. The animation will start here in condition A. So we have all the magnetization vectors lined up. They're collinear. And the net transverse magnetization is maximally. As we go through the gradient, we have dephasing according to their positions. Then we will look at displaced spins. So we have them collinear at the beginning. We have also dephasing. So this is the same. Now we'll assume that for the displaced spins, for these guys, that they will change position. So among each other, just similar to the case here. So they will be returning back, but now with different precessional velocities. Here we'll consider the static magnetization. They are not exchanging position. So when we do now, and this has happened now for these spins here nothing has happened, here they have changed position, and now we'll turn on the positive gradient. For the static magnetization, we come back to the maximum magnetization possible, but for those who have undergone diffusion, they no longer end up collinear, and now if we do the vector addition of these vector sums here of these magnetizations, we end up with a net magnetization that's not equals to 4 times here, and so the magnetization, transverse magnetization, is reduced. So this is the consequence of random motion on the MR signal. There is a amplitude reduction. This is fair to say. So let's look at this magnetization, the effect of diffusion on magnetization. I'll take another view on this. We have time here. We turn on the gradient, once positive, once negative. And we'll consider now for the time t, both with the same amplitude, but positive and negative. And we'll look at the effect on signal amplitude. So we have reduction of signal amplitude. And then when the second gradient is turned on, now it's the letter T is turning on red, then we have a echo formation. We have again dephasing during the first time period. And then when we turn on the second gradient, we have rephasing. That is in the absence of incoherent motion. That is for static magnetization. So how do we display this in terms of phase? So we'll plot the phase here for 6 isochromats, I'm sorry. The phase is being built up according to their 6 different positions during the first gradient time. So this is here. Then it stays constant during the time here between the gradients. And when we turn on the negative gradient, the slope is equal but opposite, so they all come back to the same phase. And so here they are. That means if the phase is the same for all the magnetization vectors, we have maximum amplitude and echo formation, maximum echo amplitude. So now let's look at the effect of incoherent motion. And here I'll plot a matrix of 5 by 5 voxels. We apply a gradient in the horizontal direction. So now according to that position, they are undergoing a differential phase. This is during the first gradient. And now what we have during the period between the gradients, and here we'll assume these gradients are very small in duration. This period is very long by comparison, and again, this is relatively short. So now we have no gradient during the time between the gradients, but we will assume during this time that some molecules undergo diffusion. Of course, we can not draw 10 to the 23 molecules, so I've just taken 3 pairs here that during this process we'll have assumed that they have exchanged positions to illustrate the case. This is all in the direction of the gradient, which is in the horizontal direction. Again, it doesn't matter what you call this direction, X, Y, or Z, whichever. It's just the direction of the gradient. So now these 3 pairs have exchanged positions. And when we now turn on the negative gradient, what is the effect that we see? According to the position that they have now, the phase is turned back to its original position. So for the static magnetizations, we can see here they're all collinear. These guys here, these guys, etc. They're all collinear. So that is, for them, is maximum signal amplitude. But for these magnetizations which have undergone diffusion in this animation, their magnetization vectors no longer are collinear, and therefore, if you now sum over all the 25 magnetization vectors here, the net magnetization, the amplitude has been reduced. So if I draw now this phase as a function of time with diffusion, so we'll look at the phase with the build-up, and then when we go down with a negative gradient, the slope is no longer the same for all these 6 isochromats because they have exchanged positions. So we end up at the end of the second gradient with a magnetization and phase dispersion that is no longer the same, and therefore we have at this point, because they're not all in phase, we have a reduced echo amplitude. So this is the graphical, intuitive explanation of what happens during diffusion. So now how do we describe the effect of diffusion on the MR signal in a more quantitative way? And I will do this here, and we will have a consideration on what it is that reduces the signal. Now we have to think about here, the reduction of the signal is a fact that the molecules are displaced by a certain distance during the time between the 2 gradients. This distance of displacement is the sole mechanism by which the amplitude is reduced, because when we refocus with the gradient, they are at a different position, and the difference in phase compared to the initial phase is what reduces the signal. So what are the factors that reduce the signal amplitude? One is, of course, the strength of the diffusion process. If the diffusion process is very strong, that is, the molecules diffuse easily, then we have a larger displacement. So it's the diffusion process, and this is the diffusion constant. Now, if we look at an experiment with a positive gradient here of amplitude g and a negative gradient of same amplitude g, The duration of the gradient is small delta, and they are separated by a time big delta. Then what is the next factor that influences the distance between at the beginning and at the end of the experiment, the mean distance? That's the time between the dephasing and rephasing gradient. That's the time big delta. And finally, the phase is also dependent on the strength of the gradient. It's not precisely not just the strength, but it's the integral of the gradient. So if we have a strong gradient for a long time period, the magnetization vector spread out much more. And then we apply the same gradient, so for the same position, the phase difference between original position and end position is going to be bigger, and therefore the signal is stronger attenuated. So it's the area of the dephasing gradient that influences as well the signal reduction. Now this is the example of a gradient echo that's sensitizing the diffusion process. Now I'm going to give you the mathematical formulation of this, but not the derivation of this. We're just going to concern ourselves with the result of this process. So the attenuation of the signal due to diffusion in the direction of the gradient. Of course, if there's diffusion perpendicular, we won't be able to measure that. There's no influence on the signal phase. Is actually described by a signal in the absence of diffusion as 0, that's this term here, times e to the minus bd. That's a simple equation, and it's an empirical equation. It works very well for a free liquid that is like the colored dyes that we have seen. D is the diffusion process, B is an experimental parameter, and B is the so-called B factor, or B value, and here is the exact value given. So it's first the accrued phase, so it's gradient times duration times gamma squared times big delta minus small delta over 3. So if the small delta is small, the duration of the gradient is small compared to this time, then this is essentially the duration. This is the gradient area, that's this area here, squared. That's the B factor. And like I said, I don't want to go through the mathematical derivation of this expression here. Will just satisfy us with the equation here. So B is the parameter that the operator can choose. We can choose the delta, the big delta, we can choose the small delta, and we can choose the gradient strength. That's the experimental parameter that we can choose, and D is describes the diffusion process. Now in this case, it's not the self-diffusion coefficient in magnetic resonance. It is called the apparent diffusion coefficient, or ADC, because it's an apparent diffusion that one measures, and it is not necessarily the true diffusion of the molecule. Although in the case of free water, for example, we can very well quantitatively measure this ADC, and from the ADC measurement, because this changes with temperature, we can actually determine to a very good precision the temperature of the water sample. Now the sequence that I've shown you here, that's diffusion weighting. It introduces this weighting into the signal. Can also be done with a spin echo. So we have the two gradients. Now they are positive because between them we've inserted a 180-degree pulse. So as you remember, for static magnetization, positive gradients, the effect of the 180-degree pulse is to refocus the static magnetization here. So that would be the equivalent sequence to with the spin echo. Above we have the gradient echo, and the spin echo has the advantage it is only dependent on T2, and T2 is always longer than T2 star, so one can use longer diffusion times big delta with this approach.